Okay, good morning. Let's get started with the lecture for today. So as you know, we're gonna have our first exam on Monday on the 27th. So a week from today, you're gonna have your first exam. The exam is going to be in class and it's going to include the material from the first day of classes to the material that we're gonna cover today. Okay, so up to the material that we are covering today is going to be material for the exam. So on Wednesday, what we're going to do is we're going to have a review session. So you will have, I will bring some slides with information about the format of the exam and also some questions, some problems to work during the session. And then you will have the opportunity to ask questions as part of the review. And then on Monday, we'll meet here on Monday the 27th, we'll meet here for the exam. Any questions for? Okay, good. So the lecture that follows now is the Simplex algorithm. And this is the algorithm that I've been mentioning for a long time now about an algorithm that we're going to use to solve problems that have more than 2 decision variables. Okay, so far we have learned how to formulate linear programming models using 2 decision variables. And then the last lecture, we extended that to problems that were more practical, that involve more than 2 decision variables. So the question now is, how do we solve those problems? So now we have a good understanding about formulation. We know what are the things that I needed to formulate a linear programming model. We were able to solve linear programs with 2 decision variables using the graphical method. But now let's learn how to solve these problems that have more than 2 decision variables. In this lecture, we're going to go over the mechanics, if you want to see it that way, of the algorithm, how the algorithm works. Okay, so that's what we're going to study in this lecture. And then after the exam, we're going to go and solve problems using the algorithm. So today we are not going to be solving problems. Today we're going to focus on how the algorithm works. What are the things that are, what are the steps or what's behind the algorithm that help us to solve these programs, linear programs. So let's get started. So the lecture today is the Simplex algorithm. And again, we're going to focus on those mechanics that make the algorithm work and function. So use the Simplex algorithm to solve linear programming models with more than 2 decision variables. That's the learning objective for this lecture. And this is the agenda for today. I'm going to start with an introduction, and then we are going to transition into the first step for implementing the Simplex algorithm is to convert the linear program to a standard form. So we're going to spend some time explaining what that means. And then we're going to look at transitioning from graphical to algebraic solution. So far, you know how to solve these problems using the graphical method. So now we want to transition from that with the understanding that we have about the graphical method. How do we use that information to transition to an algebraic solution? And that's what we're going to be doing today. Then after the exam, we're going to look at the Simplex algorithm, and we're going to solve problems using the algorithm. So let's talk about the introduction. For the first 3 weeks, we spent some time doing modeling, linear programs, and then solving linear programs graphically. Those were 2 decision variables problems. But most real-life linear programs have many variables, as you saw in our previous lecture. And a method is needed to solve linear programs with more than 2 decision variables. We will study the Simplex algorithm, which is used to solve linear programs with thousands of constraints and variables. So now we are extending that knowledge to these type of problems. Your linear algebra skills will now come into play. So remember what we learned at the beginning of the semester. Now we're going to be using that to apply this algorithm. So as I mentioned, before we implement the method or the algorithm, we need to learn how to set up the problem. So you formulate your problem, you remember that some of the constraints will be less than or equal to, greater or equal to, or some of them will be equalities. So in order for us to apply the Simplex method, we need to set up the problem in a standard form. And that means that we are going to set up all the constraints to be equalities. Okay, so even if you have less than or equal to constraints or greater or equal to constraints, we want the constraints to be equalities. So that's what we call the standard form. And in order to convert that, and that's needed for us to apply the Simplex method. So before the Simplex algorithm can be used to solve a linear program, the linear programming model must be converted into a problem where all the constraints are equations and all variables are non-negative. Okay, so in order for us to apply the algorithm, we need to make sure that all the constraints are equalities, or equal to, and all the decision variables are non-negative, meaning that they have a value that is 0 or a positive value. A linear program in this form is said to be in standard form. Okay, so we formulate. Now we want to solve the problem. Before we apply the algorithm, we have to set up the problem into this standard form. So what are the steps? I mentioned we're going to be focusing on the constraints and then on the variable. So for the constraints, every time that, let's say I'm calling this the I constraint, so this could be any constraint in your model. If that constraint has a less than or equal sign, then we are going to convert that constraint into an equality constraint by adding a slack variable. Okay, and you're going to see how that works in a second. And the sign restriction for that slack variable, we're going to make that decision variable greater or equal to 0. So the idea now is you have a less than or equal constraint. Right, let's say this is x1 plus x2 plus x3. and this is less than or equal to 6. The idea now is, okay, I need to make this an equality. So I'm going to use x1 plus x2 plus x3, and I'm going to add this slack variable to make this an equality. Okay, so the idea now is everything that is needed. Let's say this value is x1 is 1, x2 is 1, and x3 is 1. So the summation of that will be equal to 3. And we know that's going to be less than or equal to 6. But now we are making this an equality. So anything that is not covered by the decision variables, the original decision variables, is now going to additional value or additional weight that is needed to make this equal to 6 is going to be assigned to this slack variable. So essentially what this is saying, okay, x1, x2, and x3, let's say all of them are equal to 1, the summation equals 3. But now that this is an equality, we want S1 to assume that portion that is not covered by the decision variables. So this will make S1, how much will X1 be? 3. Okay. So again, the idea is that that slack variable is going to absorb that amount that is needed to make that left-hand side equal to right-hand side. Okay, so that's what we call slack variable. On the contrary, if the ith constraint is greater or equal to, then we convert that into an equality constraint by subtracting what we call an excess variable and adding the sign restriction EI greater or equal to 0. So the same principle now. Let's say we have x1 plus x2 plus x3, and we want this to be greater or equal to 6. Now we are making that an equality. So x1 plus x2, x3 minus E1 equal 6. So the idea is the same. We want to have at least this amount. The amount in this case is 6. So let's say this is equal to 2, 3, and 3. So now this is going to be equal to 8. In order to make this equal to 6, then we're going to have to subtract this amount, right? So this amount, E value, in this case, will be equal to 2. So let me double check. Yes. So this is 2. This is 3. This is 3. So 3 plus 3 is 6. Plus 2 is 8. So this is going to be equal to 2 in order to make it equal to 6. And that's the idea. So we are making everything equal to, all the constraints equal to something, or less than or equal constraints equal to an equality by adding a slack variable, greater or equal to constraints to equality constraints by subtracting the excess variable. And then if the variable xi is unrestricted in sign, the unrestricted sign or free variables, then we're going to have to replace xi in both the objective and constraints by this equation, where every single one of them, xi prime and xi double prime, are greater or equal to 0. And we're going to see how this works in an example. So that's when we have an unrestricted sign decision variable in our model. Yes.
So are the slack and excess variables fractional values?
No, I'm using integer values here just for the purpose of the example, but we're still dealing with fractional values in this model. We're going to deal with the integer values later on in the semester when we formulate the integer programming models. But what I show you this here with the example still applies with the fractional values. Good question. So let's look at one example. Here we have a very simple example. Leather Limited manufactures two types of leather belts, the deluxe model and the regular model. Each type requires 1 square yard of leather. Regular belt requires 1 hour of skilled labor, and the deluxe belt requires 2 hours of skilled labor. Each week, 40 square yards of leather and 60 hours of skilled labor are available. Each regular belt contributes $3 of profit, and each deluxe belt contributes $4. So we want to formulate this problem to maximize our profit. Okay, so the idea with this example is to show you how to transform these problems into standard form. So in this case, the decision variables are very simple. X1 is the number of deluxe belts produced weekly. X2 is the number of regular belts produced weekly. So the appropriate LP or linear programming formulation is as follows. So we have the maximization of the profit, and then we have two constraints, one for the leather constraint, and then one for the labor constraint. As you can see, in this model, we had two less than or equal constraints. Both of our decision variables are greater or equal to 0 because we want to produce at least 0. So we want to convert the leather and labor less than or equal constraints to equalities. So we define it for each constraint, a slack variable Si, and we are using I to denote the ith constraint. So if we have 3 constraints, I is going to be 1 for the first constraint, I is going to be 2 for the second constraint, and I is going to be 3 for the third constraint. We need to make sure that if we have 3 slack variables, that each one of them has a different number, a different name, in this case represented by a number. Because if we assign the same number to all of them, then it's the same decision variable. We need to have a different decision variable, a different slack variable for each constraint. And you will see now that in this example. So in this case, we need 2. We need 1 for the leather constraint, and we need another one for the labor constraint. A slack variable is the amount of resource unused in the ith constraint. So as I showed you in the previous slide, if we don't get to 40, let's say on the leather constraint, we only use 20, then that slack variable is going to represent the unused amount of leather. In that case, that will be 20. Labor constraint, if the left-hand side, we only use 30, then the slack variable is going to tell us this is the unused amount, which is also 30. Okay, so that's the meaning of the slack, is that unused resource in the model. So the LP is not in standard form. So that's the same formulation that I showed you on the first slide, on the previous slide. So now we want to formulate this in standard form. So the constraints are going to look like this: X1 plus X2 plus S1 is going to be equal to 40. And then we had 2X1 plus X2 plus S2 equals 60. And then X1, X2, S1, and S2 greater or equal to 0. This last one? That one is for, this is like saying X1 is greater or equal to 0. X2, yes. So they don't have, yeah. So to answer the question, no. For the decision variables, we just want them to be positive in this case. but they are not considered a constraint in that sense of adding a slack. Question. Yes, those are bounds for the decision variables. So for now, we're just focusing on the constraints. So as you can see now, we have two slack variables. What I want you to understand from this example is that there's an S1 for the first constraint and then an S2 for the second constraint. So we have two slack variables. They are different, they're named different. They're representing two different things because they are associated to different resources. So if you use the same decision variable, let's say you use S1 for both of them, then that is representing something else. Okay, so you're using the same slack to model both constraints. That's not what we want. We want a separate decision variable for, or separate slack for each constraint. It's associated to each constraint. So in this case, we have two. And again, I'm using the S1 just because that's the first constraint. It doesn't have to be S1. As long as they're named different, that's fine. I'm using I equal 1 for S1 just to say, okay, this is the slack for the first constraint. S2, this is the slack for the second constraint. But as long as they're named differently, that's fine. It's okay. So here we have another example. This is coming from a previous lecture, so I'm just using that example to look at the other type of constraint, which is greater or equal to. So now instead of adding a slack, we are going to be subtracting an excess variable. So if I formulate this into the standard form, we have the minimization of z equals 50 x1 plus 100 x2 subject to 7 x1 plus 2 x2 minus e1 equals 28 2 x1 12 x2 minus e2 equals 24, and then x1 x2 e1 and e2, all of them greater or equal to 0. So again, same idea. We have two constraints that are greater or equal to. We name them differently. In this case, I'm using 1 to represent the excess variable for the first constraint, 2, E2 for representing the excess variable on the second constraint. Any questions so far? That's simple, right? So now on the next example, we have a combination of constraints. So the original constraint, the original model on the left side, we want to convert this into a linear programming to standard form. So now we have 3 constraints that are less than or equal to, and then 1 constraint that is greater or equal to. So we proceed in the same way. We maximize z, which is equal to 20 x1 plus 15 x2, subject to x1 plus s1 equal to 100, x2 plus s2 equal to 100, and we have 50 x1 plus 35 x2 plus s3 equals 6,000. And then finally 20 x1 plus 15 x2. Let me fix this so you don't get confused. So we end up with 3 slacks and 1 excess variable. So you can see here I'm using E4 instead of E1. If you use E1, that's fine. Just keeping the numbers associated with the constraint. But if you use E1, is representing the same thing. It's just a name. As long as you have more than 1 slack variable and you name them differently, that's fine. You don't want to have the same name for each constraint. Okay, good. So now we talk. Let's talk about that case in which we have an unrestricted decision variable. So here we have an example in which a baker has 30 ounces of flour and 5 packages of yeast. Baking a loaf of bread requires 5 ounces of flour and 1 package of yeast. Each loaf of bread can be sold for 30 cents. So the baker may purchase additional flour at 4 cents an ounce, or sell the leftover flour at the same price. So as you can see here, this person has 2 options to get some profit out of selling the flour that he has left over, or he needs to purchase additional flour to sell more bread. So the problem is trying to represent whether or not, if we are going to be selling this flour that is left over, or is he going to be buying more flour to bake more? So as you can see, that could be that go either way. If you sell, you're getting a negative number. If you buy, you're getting a positive number. So that in that case, and I'm going to show you the formulation in a minute, that decision variable can be modeled as a unrestricted in sign decision variable. So decision variables, X1 represents the number of loaves of bread baked, and X2 is the number of ounces by which flour supply is increased by cash transactions. So in this case, you see X2 is unrestricted because you can increase the number of ounces of supply by buying more, or you can decrease that by selling what you have as leftover. So that's why we are modeling that decision variable as unrestricted in sign. So if you see you're trying to maximize your profit, right? If you sell your leftovers, that is going to be a negative number. And that's going to be multiplied by a negative number, which is going to increase your profit, right? If you buy more, then that's going to be buying. There's a positive number. So that buying of extra flour is going to subtract your profit. So that's why this is an unrestricted in sign decision variable. Depending on the decision that the model ends up doing, that X2 value will be positive or negative, depending on what will be more, will improve your profit. Okay, so we are modeling X2 as a unrestricted in sign decision variable. X2 is going to be greater than 0 if you purchase more. X2 is going to be less than 0 if you're selling what you have as leftover, or x2 is going to be 0 if you don't buy or sell anything at the end. So the unrestricted in sign is a special case. You don't see this very often. But we have a way to, if we want to set up this problem into the standard form, we have to use two decision variables to represent one. We have to use a decision variable that is going to assume the positive, and then a decision variable that is going to assume the negative value for the standard form. So let me show you the formulation. So in this case, x2, remember from slide 7, let me just go back here. This is what I'm referring to. So if the variable xi is unrestricted in sign, you're going to replace xi in both the objective and the constraint by these two decision variables, the difference of these two decision variables, xi prime minus x double prime. So our standard form maximization of z equals 30 x1 minus c4 x prime 2 minus x double prime. So that's the substitution. However, when you do the multiplication, you know these signs are going to change. So that x2 double prime is going to become positive, and x2 prime is going to be negative. And this is subject to 5x1 minus x2 prime plus x2 double prime plus s1 equals 30 x1 plus s2 equals 5. And then we have x1, x2 prime, x2 double prime, s1, and s2 greater or equal to 0. And so this is just a modeling technique for applying the simplex method. Okay, it's not, it's just a way for us to set up the problem in a way that we can apply the algorithm. In reality, this substitution is not representing anything. Okay, it's just a way of setting up the problem so we can apply the simplex method. Yes. So yeah, that's a very good question. So once you solve the problem, you're gonna obtain values for this and this. So you have to go back to this to find the original value of x2. So you're gonna substitute this value because you're gonna obtain values for both of them. So you're gonna have to put those back in so you can obtain the actual value of x2. Say that again? No, we just substitute into the original substitution. Yes. Good questions. Okay, so now we understand how to set up these problems into standard form. Now we can go into how the algorithm works. So let's transition from graphical to the algebraic solution. Okay, so see if you can bear with me here. It's a lot of information, but that's the basic of the simplex method. So The development of the algebraic simplex method is based on ideas conveyed by the graphical LP solution, which you understand now. So in the graphical method, the solution space is the intersection of the half spaces represented by the constraints. So you remember we set up these constraints, and then we find the area where all the constraints are met. We call this the feasible region. So these are the half spaces representing the constraints. In the simplex method, the solution space is represented by simultaneous linear equations and non-negative variables. Okay, so we're still using these linear equations to find our solution space. Yes. Yes. So that setup that we did for AX equals B. Yes. So in the algebraic solution space defined by m by n equations, where m is less than n, basic solutions corresponds to the corner points in the graphical solution space. Okay, so by solving these equations, the solutions that we're going to find are actually representing the corner points of the graphical solution. And you will see that in a minute. Why is that important? Because as you saw, when we solved the algebraic or the graphical method, our optimal solutions were always in these corner points or in the borders, in the case that we have multiple solutions. So if we can identify the corner points, then we are basically finding a solution area where we know the optimal solution is going to live. Okay, so corner points in the graphical solution space. So the algebraic solution space is going to correspond to the corner points. If we have the corner points, then we can search the corner points to find the optimal solution. So they are determined by setting variables equal to 0 and solving the equations for the remaining variables. So how do we find these corner points in the algebraic solution? What we're going to do is we're going to set up some of the decision variables equal to 0, and we're going to solve for the rest. And we're going to do that for all the combinations possible. Okay, so we find, let's say we have 5 decision variables. We're going to find all the possible combinations in which we can set up some of them equal to 0 and then solve for the rest. Then this means that the maximum number of corner points is given by this expression, the combinations. When n is equal to the number of decision variables, and let's go back, n equals the m by n equation. So m is equal to the number of decision variables, and n is the number of constraints. So the graphical method versus the algebraic method. The graphical method, you remember, this is what you do. You graph all the constraints, including non-negativity restrictions. The solution space consists of an infinity of feasible points that are inside that feasible region. And then we identify the feasible corner points of the solution space. Candidates for the optimal solutions are given by a finite number of corner points. And then we use the objective function to determine the optimal corner from among all the candidates. In the algebraic method, we represent the solution space by m equations and n variables and restrict all variables to non-negative values. And we know that m is going to be less than n. The system has infinity or feasible solutions. So we're going to determine the feasible basic solutions of the equations. The candidates for the optimal solution are given by a finite number of basic feasible solutions. And then we use the objective function to determine the optimum basic feasible solution from among all the candidates. Okay, so you see how this, sounds like a lot of work, right? So we are going to be doing all these combinations. We're going to be setting up equal to 0. And then we're going to do the process. We get a list of solutions for the corner points, and then we're going to identify the best among them. So that's the idea behind the simplex method. Obviously, it's going to be more efficient than that, but that's how this works. So let's consider this following LP. So I'm using a 2 decision variable here just to illustrate how the method works. if it will be very difficult to visualize this in a space that is higher than 2 dimensions. So we're going to use a 2-dimension space. So this is the problem that we are trying to solve: 2x1 plus 3x2. 2x1 plus x2 is less than or equal to 4. x1 plus x2 less than or equal to 5, and then x1 and x2 greater or equal to 0. So by solving, we set up the constraints. These are the constraints. And then we have an optimal solution identified by this right here. Okay, so that's how you solve using the graphical method. So in this case, you have 4 corner points. Using the objective function, remember, you set up the objective function, you find that line, and then you move that line until you find the last point that is touched by that line. So by using that process, we find that this is C, the optimal solution: x1 equals 1, x2 equals 2. So that's the solution using the graphical method. Yes.
Yes, I'm going homework.
Mm-hmm.
The first question was find the same graphical method, and it wasn't visible. So I used a graphical layer to find the section for this decimal set.
It was decimal points? Huh.
So I counted around it. My question is, if you build this out,
Well, I will have to double check which problem that you're referring to specifically, because I think for those problems that I assigned, it should be easy for you to find the optimal solution. Number 1? Yeah.
I did the same thing.
Okay.
It's like roughly somewhere around 60 and 90, but then it's like roughly it's like using a query.
Okay. Yeah, so I see what you're saying. So and for this graphical method, if it is not evident, you can find the exact point, because you are graphing this by hand. So being exact is very, very challenging. I understand that. So I guess what you did was to look at the constraints, and then you make them equal and you solve for the intersection. Is that what you did in order to find the? So you were trying to find the right points, right? The correct points for the optimal solution.
I know approximation.
Okay. Yes. So the answer to the question is, for the purpose of the assignment and the exam, if you give me an approximate, that will be fine. Okay. I just want to make sure that you are close to the exact point. Okay. The way I designed the exam is it has to be something that you can see easily. Okay. So it will be an integer. What I'm saying is, for the exam, you will see an integer value, because what I'm testing in the exam is that you know how to apply the method. Okay. But in reality, yeah, finding those numbers by hand is very difficult. Still, we need to show you how that works. And then the idea is for you at the end of this semester, you are not going to be using the graphical method to solve these problems, but you understand how the method works, and then you can use the simplex algorithm. But you have a good understanding of how that works. And that's what we're trying to show in this particular lecture. So yes, good question. You cannot get the exact number. If you give me an approximate, that should be good enough for getting the right answer in the exam and the assignments as well. I understand the challenge of doing this graphic by hand. So that's not a problem. What I don't want to see in the exam is that if I ask you to solve this using the graphical method, that you try to find the solution by solving the equations. Because the idea is that you show me that you know how the methods work. Okay. And now that you have a good understanding of this, you will see that, oh, so it's in the corner points, I can just find the corner points and substitute and find the best solution. That's not the graphical method. So if I ask you to use the graphical method, use the graphical method. If I ask you to do something else, then do what is asked by the question.
So like if you use the graphical method, walking you want, identify the T is probably the best thing. You don't want them to like.
I want you to show me that you can set up the constraints and then you can find the objective function, a line for the objective function, right? And then you can use that, you can show me that that line is going to point you to the optimal solution. Okay, so for example, let's say, I mean, I'm just guessing. I don't have time to do the work, but let's say this is the objective function line. Let's go back. Okay, so this is guessing. You get this line. So what you're trying to do is you show me the objective function line and you tell me this is the direction of improvement. So if I move that line is going to tell me this is the optimal solution. But the line could be something like this, and that's why you need to be careful. Like you cannot guess. And this the direction of improvement is this. Then you end up finding this point as the optimal solution. Okay? And you can verify that. And that's what I'm saying. Like if you know that these are the corner points, you can substitute those points here, and then the one that gives you the highest value is the optimal solution. But that's not what I want you to do. I want you to show me that you can plot this line and you can identify the optimal solution by using the objective function. Yes. So the question is, how do we draw this objective function line? Okay, so yes, yes, I remember.
Section of it, it was like it talked about like shapes, which one was like the optimal point. So like I kind of zoned in on that. Like this is how we solve this graphical.
Okay, so you know how to set up the constraints, right?
Yeah.
Those lines. Okay. So now you have an objective function. In this case, this is 2x1 plus 3x2. And this is the objective function. This is what's gonna tell me the direction of improvement in my problem. Okay. So so in order for you to find a line, you need 2 points, right? Do you understand that? So 2 points, you can draw a line. So the first thing you want to do is to find 1 point, right? So you can choose any point in this area to find that first point. I'm going to choose, let's say, 1, 1, because that's a point in the feasible region. So I'm gonna, and this could be any point in the feasible region. 1, 1 is simple. It's easy for me to solve, so I'm gonna use 1, 1. So I'm going to use 1, 1 as my first point, because I need 2 points to draw a line. So if I substitute 1, 1 into the objective function, this is 2 plus 3. So this is equal to 5, right? And so I got 5. So the objective function value equals 5 when I have a point 1, 1. What I need for this line is a second point, right? But for me to find a point in the same line, that point has to have the same value for the objective function, meaning 5. Okay, so now I need to find a second point. Okay, I don't know what that second point is, but I know that that second point also, when I substitute that second point into the equation, it has to be equal to 5. Okay, I think I make things more complicated because this is a yes, prime number. But let's see how this works. So second point in which this has to be equal to 5. Yes, so the easiest way for me to find that point is to make one of those decision variables equal to 0 and solve for the other one, right? So if I make x2 equal to 0, then I can solve for x1, right? And that x1, as you say, is 2.5. So a second point that is going to be on the same line is 2.50. Because when I substitute that into this equation, 2.5 plus 3 times 0, this is equal to 5. So I have a second point is here. So now with those 2 points, I can draw a line. And if I move that line in this direction, the last point that is going to be touched by that line, if you see that, the way the shape of that line, you will move this, and you will see that that last point that is touched by that line is going to be this point. Yes.
So I can see that this line will be parallel to the other line. Therefore, we will touch 2 points.
You say it's parallel to it?
Yeah.
Yeah,
Because
again,
if you take second line, you take points, but you take 0, 5, fulfills the objection function.
you say at the third point? If we do a third point, is that what you're? Yeah, I guess for this, it looks like you're saying that.
No, I'm not trying.
Yeah. So this the direction of improvement, and that's something you know that if you move this to down, you're gonna find this point. That's not the direction of improvement. You're gonna end up with a value of 0. So you are gonna move this up because that's what's going to increase the objective function. So if you move this parallel to it until you touch the last point in the feasible region, the last point that you're gonna touch is that optimum value. Yes.
So it's actually parallel.
These two?
Yes.
Sure.
If you take x1, 0, and x2, 2.5, it's going to fulfill the injection function. And then you take 0,
If
5.
x1 equals 0, then it's 3 times. It's going to be, if you make x1 equals 0, then you have 3x2 equals 5. And then is x2 equals 5 over 3.
Oh, no.
Right? Yeah. So there's a different point. Okay. So that's how this works. And when I ask you to solve using the graphical method, I mean, I know there's a challenge on drawing these things by hand. But if you are able to show me the constraints, show me the points, show me the objective function, even if you end up, like, the worst thing that can happen in this problem is that you end up telling me that this is the optimal, but all this line also is optimal. It's a multiple solution, which in this case, that's not true. But that's the worst thing that can happen if you see that when you move this is overlapping. If the line is overlapping with this BC line, then that means that any point in this line is optimal. That's not the case here. Okay. So that's how you apply the graphical method. And again, you show me the constraints, you show me that you identify the objective function, you plot that, and then you tell me, okay, the objective function value or the objective function line is telling me that this is the optimal solution. So now that we have this understanding, as we mentioned already, the corner points are going to give you the optimal solution. We can proceed algebraically in the same way. So consider the LP with two variables. Algebraically, the solution space of the LP is represented by the following equations. So now we are transforming this into standard form. So we are adding the slacks because those constraints have less than or equal constraints. So the basic solutions are determined by setting n minus m variables equal to 0 and solving for the remaining variables. So if you remember in our discussion for linear algebra, we were able to identify basics and non-basic variables and separate them into two groups. The non-basic variables are the variables that are going to be set up equal to 0. Okay, and the basic variables are going to assume values that are different than 0. So what this is telling us is now you need to be aware of the number of decision variables that you have in your model and the number of constraints. So after you set up your problem into standard form, you're gonna end up with m equals 4 in two constraints. So that means that we can set up m minus m decision variables equal to 0. In this case, is 4 minus 2 equals 2. So we're going to set up two of them equal to 0 and then solve for the rest. For example, if we set up x1 equals 0 and x2 equals 0, the equations provide the unique basic solution s1 equals 4 and s2 equals 5. If you go to the model, to the graphical solution, that point is representing this point right here. x1 equals 0, x2 equals 0. Okay, so by setting up the problem this way, we make two of them equal to 0 and then solve for the rest. We can start identifying the corner points of our graphical solution. So we have to proceed in the same way for all possible combinations. Okay, so I now have to find the other combinations in which I can set up two of them equal to 0 and then solve for the rest. Another point can be determined by setting s1 equals 0, s2 equals 0, and then solving the resulting two equations are these two, right? So two equations, two decision variables, we can solve this. The associated basic solution is x1 equals 1, x2 equals 0. And that point, when we make s1 and s2 equals 0, that means that's no slack, right? No slack in this model. We are using all the resources. So that gives us x1 equals 1, x2 equals 2, which, if you remember, that's the optimal solution. So what's telling you is that if you make use of all your resources, you should be able to get the optimal solution in your model. It's not always the case, but most likely that could be your optimal solution. You probably are wondering which variable should be set up equal to 0 to target a specific corner point. Without the graphical solution space, we cannot specify the m minus m 0 variables associated with a given corner point. So this is getting into how the simplex method works. So if you know where you are and you change one of those decision variables from a non-zero value to a 0 value, you can understand where you're heading. You are moving from point to point, and if you want to find the direction of improvement, you can direct your search using these combinations, which is what the algorithm does. So the solution is consider all combinations in which variables equal to 0 and solve the resulting equations. The optimal solution is the feasible basic solution or corner points with the best objective value. Non-basic variables are the 0, m minus m variables. The remaining variables are called basic variables. The solution obtained by solving the equations is referred as to the basic solution. Okay, so what we're gonna do is after we set up n minus m, n equals the number of variables, m equals the number of constraints. We find how many variables we can set up equal to 0, and then we start solving for all possible combinations. At the end, we look at the list for the solutions, and we get the one that maximizes or minimizes our objective function. That's going to be the optimal solution. So if I do that process for this problem, these are all the possible combinations. Have the non-basic, which are the 0 variables. So these are the possible combinations for these 4 variables. The basic variables are the ones that I'm going to solve for. And the basic solution, and the associated point. So what this is saying is basic solution S1, S2 equals 4 and 5. The associated point is A, which is this point right here. This is A. And how do I know that this is the point? Because that's where these variables are equal to 0. So X1 and X2 are the ones that are showing in this graph, right? S1, S2 are not part of this graph. I'm plotting the points using X1 and X2. For the first case, I'm making them equal to 0. So I know from the beginning that this is representing this. The objective function in that case is equal to 0. So what this is saying, if you think about it from a practical perspective, I'm not using any resources because my slacks 4 and 5 are equal to the right-hand side. So I'm doing nothing. And that's why the solution is equal to 0. I'm not using my resources. There's no way I'm making any profit. Okay. Then I find X1 and S1, make them equal to 0. So the basic variables, these are the ones, X2 equals 4, S2 equals minus 3. What happens with this solution? Do you see a problem here? It's a negative value. Yes. So that solution is not feasible, right? Because when I solve this, it's a negative value for my slacks, and when I formulated the standard form, I made them greater or equal to 0, all of them. They need to be non-negative. So this is not feasible. Associated corner point, what this is representing is this point here at the top. As you can see, that's not part of the feasible region. Okay, so it's not a feasible solution. X1 and F2, you get this point. Yeah, that's point B. This point right here, point B associated here. You mark here. I have point D following that one, and then point E is also not feasible. E is not feasible. F is not feasible. F is here at the top. And then finally, I find point Z. So after looking at all possible combinations, I have this column here for the objective value. As you can see, I'm looking for the maximum solution. So from that list, the best solution or the optimal solution is 8, which corresponds to these decision variables and these values, which is this point right here. So again, by using this algebraic strategy, I can get to the optimal solution. If you apply the graphical method, I think you will do it faster. Remember, the idea is that we are now transitioning to solving this graphic algebraically, so we can solve problems that have more than 2 decision variables. I have another example. So this is the preview of the simplex algorithm. So let's look at that. So based on everything that we have discussed so far, this is the general form for an LP. Suppose that an LP with m constraints and n variables has been converted into standard form. That's what we are representing here. The form of such an LP is this one. So going back to the linear algebra, now we have this A matrix well, representing the coefficients. We have the vector for the decision variables x, and we have a vector for the right-hand side, which is b. Ax equals b. Okay, and we have another vector of coefficients for the objective function. Those coefficients are c1, c2, and cn, up to cn. So this is the standard. You see all the constraints are equalities. If we define these matrices, and vectors, this is how the model will look like. The constraints may be written as a system of equations, ax equals b. Consider a system ax equals b of m linear equations in n variables, where n is greater or equal to m. Basic solution to this system is obtained by setting n minus m variables equal to 0, which is what we did in the example, and solving for the remaining m variables. This assumes that setting n minus m variables equal to 0 yields a unique value for the remaining m variables. To find a basic solution to ax equals b, we choose a set of n minus m variables, the non-basic variables, and set of each of these variables equal to 0. So we look at minus m, that number is going to tell me how many variables are going to be equal to 0. I choose a group of that size, and those are going to be my non-basic variables. Then we solve for the values of the m minus m variables, which equals n. Those are the basic variables that satisfy ax equals b. Different choices of non-basic variables will lead to different basic solutions. And this is summarizing what we did. So consider the basic solutions to the following system of equations. We have these two equations, the number of non-basic variables. We have 3 decision variables and 2 equations. That's going to be equal to 1. So setting, for example, in non-basic variable x3 and basic variables x1 and x2, we get this solution or this system of equations. We can obtain the values for these basic variables by setting x3 equals 0. We solve the rest, so we get x1 equals 2 and x2 equals 1. Thus, x1 equals 2, x2 equals 1, and x3 equals 0 is a basic solution. So this is, again, explaining, I guess, in more elegant way what we just did for the previous example. Okay, we set up, we have these many constraints, these many decision variables. We look at the difference, number of decision variables minus the number of constraints. We find that number, and that means that that number of decision variables can be made equal to 0, and we can solve for the rest, which is what we did here. If the non-basic variable equals x1, which is 1, and then we solve for x2 and x3, we can find another solution. If we let x2 equal 0, we can solve for x1 and x3, and the basic solution is here. So you can see -1, this is not feasible. Some set of m variables do not yield a basic solution. If we choose this, consider the following linear system. If non-basic variable x3 and basic variables x1 and x2, the corresponding basic solution will be this. So this system has no solution. Doesn't matter what number you put there, you're not going to find an x1 and x2 value that gives you x equal to 1 for the first equation or equals 3 for the second equation. So in this case, there's no basic solution corresponding to basic variable x1 and x2. Any basic solution in which all variables are non-negative is called a basic feasible solution. For the basic solutions on the previous slides, x1 equals 2, x2 equals 1, and x3 equals 0, and x1 equals 0 are basic feasible solutions. But if you remember, I showed you a case in which you have a -1. This fails to be a basic feasible solution because this value is negative. Adjacent basic feasible solutions. So for any LP with m constraints, 2 basic variable solutions are said to be adjacent if the sets of basic variables have n-1 basic variables in common. Okay, so this is leading into how the simplex works. So if I find a solution that is better than the previous one, I can use this strategy to identify another solution that is close to this one and see whether or not that's going to improve my my solution. So that's what we call, out of these sets, if I'm here, I can find which other points are close to this one and see if those points are improving. If that's the case, I move to that one. If that's not the case, I still here, and then I search for another solution. So know that two basic feasible solutions are adjacent if they both lie on the same edge of the boundary of the feasible region. So for example, in the leather limited LP, the basic feasible solution corresponding to point E is, so that's this point, is adjacent to the basic feasible solution corresponding to point C. Okay, so I know those lie on the same line. These points share n minus 1 or 2 minus 1 basic variable, x1. Points E, basic variables x1 and x2, and are not, so point E and point F, which is here, they are not next to each other, and you can see that in the graph because they don't share any basic variable. So if they share a basic variable, they're next to each other. If they don't share a basic variable, they are not next to each other. So if I go through that process, I can identify all the combinations of non-basic and basic variables. I can solve for, I set up the non-basic equal to 0 and then solve for x1 and x2. And I can find the basic feasible solution for each one of them and then identify the corresponding corner point for that one. Okay, so I'm going to stop here. Again, this is a preview for the simplex method. There's an assignment that is asking you to do this. It's posted today, or it's going to be posted today. That's going to be it's just one problem. That assignment has one problem. And we're going to discuss that problem on Wednesday. So it's just for you to get ready for the exam. So any questions? No, it's going to be an assignment. It's going to be due the day of the exam. But we're going to discuss the problem in class on Wednesday. Okay. Any questions? Yes. No, the exam is going to be closed notes, closed book. So the only thing that you can have with you is your pen and eraser. Anything else, it's not needed. If you need an equation, I will provide it. I will let you know on Wednesday because I'm working on the exam now. So if it is needed, I will let you know. Yep. Good.
So like the limitations to this algorithm, and if you had more than questions, one of them would couldn't find a combination.
You should, if you meet the MN, if you have more decision variables than constraints, you should be able to find it. Yeah, it's just that's more tedious. You will have to do a lot of math. Yes, so too many combinations. And that's why we are showing the example with the two decision variables. You get the idea, and then we transition to the algorithm, which is cutting some of those steps by a lot. Okay, good, good. Talk more on Wednesday. Welcome.